Alright, for problems 11 through 14, we're going to draw a single card at random from a standard 52 card deck. Find the odds against its being each of the following. So keep in mind, I'm even going to write it down to make a big deal out of it. This is odds against. Okay, so odds against being a heart. So how about odds for being a heart? That's going to be second. How many hearts do we have in the stack? Remember, there are 4 suits. There's diamonds and hearts and spades and clubs. And there are 13 of each suit, which means there are 13 hearts. Okay. How many are not hearts? So I take my 52 cards and I subtract 13 from it. And that's going to give me, what, 39? So 39 to 13 is odds against being a heart. Okay? Now you've got to reduce. So there's a value that divides into both of them, and that just happens to be 13. So 13 divides into 39 3 times, and 13 divides into 13 1 time. And that's how you should write your odds for and against. Odds and probability are always in the lowest terms. So if these values have numbers that divide each, you need to do that. And again, to check yourself, you could add these two numbers together, and that should give you the 52 card deck. Now here we are again, same directions. We're selecting one card from a standard 52 card deck. We want to find the odds against it being a red queen. Okay, so we know we're writing against first, and then you write 2, and then odds for. Now, how many red queens are in the stack? And you probably know this by now. There's just one. Actually, back up. There's 2 red queens, right? So there's a queen of hearts, and then there's a queen of diamonds. There are 2 other queens, but they're black. So there are 2 red queens. Now, if we pull out those 52 for, how many are left over against? Well, 50, right? So 50 of those cards are not red queens. 2 of those cards are red queens. Now, once again, there's a greatest common factor here. 2 divides into both of these values. So 2 goes into 50 25 times. 2 goes into 2 1 time. And there's your odds against selecting a red queen. 25 to 1. So we're going to choose a single card from a standard 52 card deck. Find the odds against an ace. Okay, so again, if it's odds against, you write against is the first number. So basically not an ace. And 4 is the second number, which is an ace. And then you just go counting cards. So how many aces do we have in the stack? 4. How many of them are non-aces? The rest of them, which is 48. So 48 out of the 52 are not aces. 4 out of the 52 are aces. Notice if you add these numbers back together, you get the total of the 52 cards. But 4 divides into each of these. So we have a greatest common factor of 4. 4 divides into 48 12 times. 4 divides into 4 1 time. So the odds against drawing an ace are 12 to 1. Okay, so we're pulling a single card out of a 52 card deck. We want to find the odds against a king or a black face card. And remember, or really means add. So we have a king. Notice there are 4 ways to get a king. And if you go look at your stack of cards, I'm not including it in the picture here, but go look at the stack that we've listed before. And how many of them are black face cards? Well, there are 12 face cards in the stack. Let me explain. There's a jack, queen, and a king of hearts, a jack, queen, and a king of diamonds, a jack, queen, and a king of clubs, and a jack, queen, and a king of spades. I can't draw spades very well. There you go. All right. Now, we've already counted 4 kings over here, so I can't count any of these. I've already counted them, right? And I can't count the hearts or the diamonds because those are not black cards. The only black face cards we have not already included on our list are the Jack and Queen of clubs and of spades. So that's plus 4 other cards. So there are 8 on the 4. So if you're a king or a black face card, there's only 8 cards in the deck that meet that criteria, which means 52 minus 8 is going to be 44 against. So there are 44 cards that are neither a king or a black face card, and there are 8 cards that are either a king or a black face card. Okay? So if I count them over here, that's a king, that's a king, that's a black face card, and those are black face cards. So is that 8? No. Oh yeah, I forgot to highlight these kings. Now it's 8. Okay, so definitely 8. And now we need to read. Y'all, I think the video did weird on me. Anyway, so 44 is against, 8 is 4. I divided both of those values by 4. 44 divided by 4 is 11. 8 divided by 4 is 2. And my final outcome for odds for or against drawing a king or a black face card are 11 to 2. And for problems 15 through 18, a pair of dice are rolled. Find the following. Now remember when you roll a pair of dice, you'll list all the outcomes. It's worth taking the time to write out. Remember, across the top, this is kind of like when we selected numbers in the beginning. I need a pen that works. Across the top, you could have a 1, a 2, a 3, a 4, a 5, or a 6. That represents all the possibilities of the dots on the die. And then 1, 2, 3, 4, 5, 6. So you could roll a 1, 1, a 1, 2, a 1, 3, a 1, 4, a 1, 5, and a 1, 6. Now I'm going to pause the video and finish this so we can discuss this problem. Here we go. It takes a couple of minutes. You don't have to write it perfect, but it helps with problems. So anytime you roll a pair of dice, it helps to see all 36 outcomes right in front of you. So we're trying to calculate the probability of doubles, which is the same number on both dice. Okay, now you'll see doubles right down the diagonal from top left to bottom right. How many outcomes is that? Right, so count them 1, 2, 3, 4, 5, 6. Now there are double 1s, double 2s, double 3s, 4s, 5s, and 6s. So there's 6 out of the possible 36 outcomes, and we know 1 divided by 36 is 1/6, and there is your probability. Now I haven't been using notation like I should. I should say that the probability of rolling doubles is equal to 6 out of 36, which is 1/6. Now for 16, they're asking for the odds in favor of a sum greater than 2. Still the same experiment. I'm going to flip to the previous page, or the previous slide where we wrote all 36 possible outcomes. But let's think about this before we move on. The odds in favor of a sum greater than 2. So what we need is 4. So 4, a sum greater than 2. And then we need against a sum greater than 2. Okay, we'll count them. They should total to 36. So first of all, let's go back and look, and how many have a sum greater than 2? So we go back, and remember the sums are on the diagonal. So this sum is 2, this sum is 3, this sum is 4, this sum is 5, this sum is 6. You get the point. Now, greater than 2 means everything but that first one. Right? That's a sum equal to 2, not greater than 2. But everything else is bigger than 2. 3, 4, 5, 6, all the way down here to 12 when you add those two together. So 4 greater than 2, remember if we write that down, 4 greater than 2 is going to be 35 of them. Against greater than 2 is just the 1. Remember, that's just the 1, 1 outcome, and this is all the other ones, okay? So 35 to 1 is 4, a sum greater than 2, because one of those is equal to 2. Notice it does add back to 36, our total. So problem 17 is asking about the odds against a sum of 7 or 11. Against, right? So we're doing against, that's how many that are not equal to 7 or 11. And then 4 goes over here because it said odd against, so we write against first, and that's 7 or 11. And we'll go back and look at our list and just count. First, let's count how many of them are 7 or 11. Okay? Now, as to not confuse, I'm going to get rid of some of these lines I got going on over here, and let's highlight the diagonal that has a sum of 7. Remember, that's 6, 1. I didn't mean to do that. Okay, there we go. So that's 6, 1, 5, 2, 4, 3, 3, 4, 2, 5, and 1, 6. Those are add to be 7. Where's the 11 diagonal? Well, close to the 12. 12's at the end. 6, 5, and 5, 6. So all those that I highlighted in green are a sum of 7 or 11. So how many is that? 1, 2, 3, 4, 5, 6, 7, 8. 8 of these guys is a sum of 7 or 11. Okay, so that's going to be 8 over here. That means the rest of them are not a sum of 7 or 11. Remember, there's 36 total. So if I do 36 subtract 8, that's going to give me 28 that don't add to 7 or 11. We could count them. So you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's harder to do. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, and down here's 28. Yeah? Okay, I got it. I think it was easier just to subtract. Don't forget to put the 2 in between. So 28 to 8. And also, don't forget to divide each of these by a greatest common factor, if it's possible. These both divide by 4. 28 divided by 4 is 7. 8 divided by 4 is 2. 7 to 2 is my odds. Alright, for this problem 18, they want the probability this time. Notice it's not the odds, it's the probability of the sum that is even and less than 5. Now when you do probability, let's use proper notation. The sum is even or less than 5. Now we could just go count those. How many total do we have? 36. We know there's 36. Now, if we just count the ones that are even or less than 5, let's go back and look. And I'm going to highlight, let's do different colors, okay? Even means they add to be an even number. For example, 1, 1 is even because it adds to be 2, but 2, 1 and 1, 2 add to be 3, so I'm not going to highlight it. 3, 1, 2, 2, and 1, 3, they add to be 4. But the next diagonal adds to be 5, so I'm not going to highlight it. But 5, 1, 4, 2, 3, 3, 2, 4, and 1, 5 add to be 6. Whereas that longest diagonal, 6, 1, all the way through 1, 6, adds to be 7, which is odd. But even up here again adds to be 8. 6, 2, 5, 3, 4, 4, 3, 5, 2, 6. The next diagonal adds to be 9, so I'm not going to highlight it. But 6, 4, 5, 5, and 4, 6 add to be 10. And finally 6, 6 adds to be 12. Okay? But what was the other thing they said? It says the probability of a sum that is even and less than 5. Both of those things need to be true. Even and less than 5. So you know what? I'm going to go back and look. This time let's highlight even and less than 5. So 1, 1 is both even and less than 5. 2, 1 and 1, 2 are less than 5, but they're not even. 3, 1, 2, 2, 1, 3, they're even and less than 5. Okay? 4, 1, 3, 2, 2, 3, 1, 4, they add to 5. So they're actually neither one. It's not even and it's not less than 5. So how many really outcomes do we have? Just the ones that I highlighted for both. Remember, and means both of those things have to be true. So it's 1, 2, 3, 4 outcomes out of the possible 36. Now, again, not allowed to leave probability or odds where there's a greatest common factor. 4 divides into both of these, so 1 and 4 divides into 36 9 times, right? So 4 into 4 goes 1 time, 4 goes into 36 9 times. Our probability reduced is 1/9. Okay, folks, so we've got 32 cards. I'm at 32 cards. 2 cards are drawn without replacement from a standard 52 card deck. Find the probability of each event. So we're going to draw 2 cards. We're not going to put them back in the stack. And we're going to find out the probability that both cards are red. Okay, so let's just think about the first card, if that's possible, and then multiply it by the second card. Now, why are we multiplying instead of adding? Because it says the first card is red and the second card is red. Now, I know there's not an and written in here at all, but it's implied. If both cards are red, that means the first card is red and the second card is red. Now, if we draw the first card, you know, it's going to be out of 52, right? But it needs to be red. So how many red cards are in the stack? Half of them. So 26 out of the 52 are red. Now, the second time we draw, we don't have as many cards available because we've already drawn out a red card, right? So there are 51 cards in the stack now. How many red cards are in the stack? There's only 25 because we've got to assume we've already drawn a red card. And now we can multiply these together. Now, if you're doing this by hand, okay, 26 and 52 reduces. 26 divides into both of those. So that's like 1/2 times 25 divided by 51. That makes it easier to multiply. 1 times 25 is 25. 2 times 51 is 102. And I don't see that there's any common factor there at all. So that would be my probability that you got 2 red cards. Okay? And notice this problem is just slightly different. Problem 20, we're still drawing 2 cards without replacement from a standard 52 card deck. Both cards are the same color. So think about what that means. That means both cards are black. Write that down. So both black. Or, right, or both are red. So let's calculate them both being black. So if they're both black, it means the first one's black, which is 26 cards out of 52 cards. And the second one's black, but we don't have 52 cards to choose from anymore. There's only 51, and we don't have 26 black cards to choose from. There's 25. Or means add, right, y'all? Both are red. We did that already, but we could do it again. When you choose the first red card, it's going to be 26 out of 52 times the second red card. There's only 25 left out of the 51. Now notice these are the same probabilities for both of them. If you did problem 19 with me, you could have just multiplied that by 2. But I wanted to do it all the way through just in case you didn't do 19 with me. So 26 divided by 52 is actually 1/2 times 25 over 51. Same thing over here. 1/2 times 25 over 51. That's 25 over 102 for both of these multiplication of fractions. 25 plus 25 is 50 out of 102, but that will reduce to 49. No, it won't. It'll reduce, but not to that. 50 divided by 2 is 25. 102 divided by 2 is 51. So there are 25 out of 51 chances that both cards are the same color if you randomly draw 2 cards out of a standard 52 deck. Okay, so we're still drawing 2 cards without replacement from a standard 52 card deck. Let's find the probability that the second card is a queen, given that the first card is an ace. So what this is saying is you're drawing 2 cards. The first one is an ace. You already know the first one is an ace. What is the probability that the second card is a queen? So again, this is a given problem. And the given problem, usually your sample space is restricted. So this, again, if I use the proper notation, this is the probability that your card is a queen, given that your first card is an ace. Okay? Now, the ace is going to narrow down our sample space. So we had 52 cards to start with, but we drew out an ace. So how many cards do we have left, y'all? 51, right? 51 cards. How many of them are queens? You know, there are 4 queens, 4 jack, 4 tens, 4 of everything in a standard 52 deck. So there are 4 queens remaining out of those 51 cards. So your probability is 4 out of 51. That fraction doesn't reduce, so there's your probability. All right, so our last problem of the 19 through 22, where we draw 2 cards, we don't put them back in the pile without replacement. From a standard 52 card deck, find the probability of each event. This time, the first card is a face card, and. This and is very important, right? And the second card is black. If you'll remember, and means multiply. So we're finding the probability that the first card is a face card. And the second card, okay, is black. But it's black given that the first card is a face card. Because remember, the first card's a face card. But the problem is this happens in like a couple of different ways. So let's think about it. The first card could be a face card. And the second card could be black, and they could not have anything to do with each other. Like, what if the first card was a red face card? That won't change the number of black face cards in the pile, right? Or black cards in the pile. But if the first face card is a black card, that will change the black cards in the pile. So we have to break this down in two different cases. Oh my goodness. So the first card is a face card. What if it is a red face card? So it's the probability of a red face card times the probability of a black card given a red face card. What's the other way it could happen? What about the probability of a black face card first? And then we'll multiply that times the probability of a black card given a black face card. And I know these probability questions can kick up there quick, can't they? Okay, so that's what's happening. There's two different ways this can happen. And see, the probability is different for each of these. And that's why you have to calculate it separately. And the reason we're adding is because it can happen this way or it can happen this way. When you talk about it could happen this way or that way, then you need to add. But when it says and, when you have to do both things, you need to multiply. And that's why this is multiplied and why this is multiplied. Now let's see if we can think our way through this. First of all, what's the probability of getting a red face card? Now, I probably need to remind you again. So the face cards, there are 12 of them total. I'm going to put this top right. There's a jack, a queen, and a king of diamonds, and a jack, queen, and a king of hearts. But then there's black ones also. There's a jack, king, and a queen of spades, and a jack, king, and queen of clubs. That's all 12 of our face cards right there. So the probability of getting a red face card, well, there's only 6 of them, right? So it's going to be 6 out of 52 cards. That's our first card. Times. Now, we've got to assume that we pulled out that red face card. So now there are only 51 cards left in the deck, right? We pulled out one red face card. So there's 51 cards left in the deck. And now we want a black card. Now how many black cards are in the deck? 26, right? There's 26. Did we pull one of them out to start with? Nope. We pulled out a red face card. So that's going to be times 26 over 51. You with me? Maybe? Okay, plus, because of our or. Now let's do this again. This time we're going to pull out a black face card. How many black face cards are there? Let's go to the top right of the screen. There are 6 of them. Just like there were 6 red ones, there's also 6 black ones. Okay, now, because we pulled out a black face card, there's only 51 cards left in the deck. And because we pulled out a black face card, there's one less black card in the deck also. Now there's only 25 black cards left in the deck. So remember, there are always 26 red cards, 26 black cards. When you pull a red card out, there's still 26 black cards left in the deck, but only 51 cards because we pulled out a red face card. Here, there are 6 black face cards, just like there were 6 red ones. We pulled a card out, so there's only 51 cards left. But since we pulled out a black card, out of those 26, there's only 25 left. Now, over here, I can simplify. 26 goes into 52 2 times. I can even do more than that. 2 goes into 6 3 times. That gives me 3 out of 51. Ooh, 3 even goes into 51, y'all. 3 goes into 51 17 times? Is this 1 out of 17? I think it is. Don't worry, I'm going to check it on my calculator. Yeah, that's 1 out of 17. Now, listen. If you don't want to do any of that simplifying nonsense, you know how to do this. 6 times 26 over 50, 2 times 51, and simplify it to lowest terms, or use your calculator to simplify it all the way. Now, over here, I see things in common. 3 goes into both of those. 3 goes into 6 2 times. 3 goes into 51. We already established that 17 times. 2 goes into 52. So I can take that a 1 and that to be a 26. And I don't think anything else simplifies. So 1 times 25 is 25 over 26 times 17. Hold that thought. Hey, wait, I decided I don't want to multiply this 26 times 17. Let me show you why. Not yet. Because I need a common denominator to add these together. If I multiply that out, I'll have to work to find it. But if I just multiply the other side by 26 over 26, we'll have a common denominator. So to finish this out, this is 26 plus 25 over 26 times 17. Now we know 26 plus 25 is, what, 51. That's not bad. 26 times 17. Hold on. I still decided I didn't need to multiply 26 times 17 because look, 17 goes into 51 3 times. And that's 3 over 26, and that will not reduce anymore. So your final probability for that is 3 out of 26. All right, folks, let's talk about TED. So problems 23 through 26, TED has a 0.78 chance, or 78/100ths chance of making par on each hole of golf that he plays. Today, he plans to play just 3 holes of golf. Find the probability of each event. Hey, typo. I just noticed it. So each. Oh, great. Ignore all that. Sorry. Of each event. I'll fix that in a minute. Round your answers to 3 decimal places. So Ted makes par on all 3 holes. So that means the first hole he makes par. So there was a 78%, or 0.78, or 78/100ths chance. The second one, does the second hole have anything to do with the first hole? No, it's just the second hole, so 0.78. And then the third hole would also be 0.78. You just multiply those 3 together, and we're going to get an answer of 0.475. Let me tell you the exact value. Okay, I got 0.474552, but again, notice it said round 3 decimal places, so that's 0.47. I already gave it away that it was 5, but we're looking at this decimal place. Only look directly to the right. If that's 5 or larger, that guy goes up. So 0.475, or 47.5%, or 475 thousandths is the probability that he makes par on all 3 holes. Okay, so Ted can make par 0.78 is the probability, or 78/100ths of the time. We want to know the probability that he makes par on exactly 2 of the 3 holes. Once again, the book and I differ a little bit on this, but let's see if we get the same answer. So let's think about how this could happen. So he can make par on hole number 1 and hole number 2, and then not par. Let me make this more clear. Hole number 1, hole number 2, hole number 3. He can make par and not par. But that's not the only way it can happen. He could also, notice the or he can make par on the first hole, not par on the second hole, and par on the third hole. What's another way it could happen? Well, he could not make par on the first hole, but then he can make par on the second hole and par on the third hole. This ought to remind you of employees picking days of the week. It's very similar. So par on the first hole is 0.78. Par on the second hole is 0.78. Hey, what's not par? If he makes par, the only options is he makes par or he doesn't. So to get not par, it's going to be 1 minus 0.78, right? Which is 0.22. So we multiply those together, plus, again, par on the first hole is 0.78. Not par on the second hole is 0.22. par on the third hole is 0.78 plus, okay, not par on the first hole is 0.22, par on the second hole is 0.78, and par on the third hole is 0.78. So really I'm just calculating the par for each hole that he's doing. But since there are options when they say exactly 2 of the 3 holes, then I have to work it around. So first and second hole, first and third hole, or second and third hole. And that's the only way it can happen. But notice it's the same values I'm multiplying together. 0.78 twice times 0.22, just in different orders, but you're going to get the same answer. So it's really 3 times 0.78 times 0.22 times 0.78. Okay? And that gives me an answer of 0.401544. Now that's what showed up in my cell phone. I'm not even using a calculator. And I was just around to 3 decimal places. Doesn't it say that? Yes, around 3 decimal places. This is my third decimal place. Again, directly to the right is a 5. So this is approximately 0.402 or 402 thousandths. Hey, it's almost half, right? 0.5 is half, so it's a little just under half that he will make par on exactly 2 of the 3 holes. Okay, Ted's playing golf. He's got a 0.78 chance of par on each hole. We didn't want to know the probability that he makes par on at least 2 of the holes. You know, whenever you see at least, think about what that means. At least 2 of the 3 holes means, make sure my pen is working, 2 of the holes, or 3 of the holes. Okay? Hey, we've calculated that. Exactly 2 holes, and we've calculated that. Let's go back and find the exactly 2 holes. That is problem number 24 right there, 0.402. So I'm going to fill in that information. That's 0, in my pen, 0.402. Or, then we add 3 holes. Didn't we calculate that he makes par on all 3? We did. Problem number 23, 0.475. So that it would be 0.475. I add those 2 values together, and that should be my answer, which is, in my head, I can even do that, 0.877. So the probability that he makes par on at least 2 of the holes is 0.877. Well, what about this problem? He makes par on at least 1 of the 3 holes. Let's think about what that means. At least 1 of the 3 holes means 1 hole, or 2 holes, or 3 holes. Right? So you could calculate those separately. We've already calculated the 2 holes or the 3 holes, so you could calculate the probability of 1 hole, or you could calculate the complement of this. What is the complement? Now, sometimes the complement's not worth doing. But when it's a simple thing, it is worth doing. And not 1 hole or 2 hole or 3 holes means par on none of the holes, right? And when you do complement, you do 1 minus what the complement is. Okay, so 1 minus par on none of the holes. That means the first hole he doesn't make par. Remember, that's 0.22. Because if 0.78 is he makes par, then 1 minus 0.78 is 0.22 that he doesn't. That's 0.22, not what looks like 7222, like that. So it's going to be 0.22 on the second hole and 0.22 on the third hole. So when you calculate that, 1 minus, that's 0.22 to the third, which is going to give you, stand by, I went ahead and wrote it all down. So 0.22 to the third is 0.010648. 1 minus that is 0.9893 and some more stuff. But since we're rounding 3 decimal places, I just chopped it off at 0.989. So it's very likely that he will get at least one of the holes par. And then the last problem, which to me, the way I've been doing these others, this one's probably easier. He makes par on the first and the third holes, but not on the second one. So if he makes par on the first hole, that's 0.78. If he makes par, he does it on the second hole, so that's 0.22. And then he makes par on the third hole, that's 0.78. Now, I can do that because each time he golfs a hole is completely independent of the hole before. What he scores on the next hole is not dependent on how he does before. Now, we know psychologically that might not be true, but we're just saying if he has a 0.78 chance every time of making par, then the next hole or the previous hole does not affect that hole. Then I just multiply these together. And if, again, I use proper notation, he makes par on the first and third holes. So first and third. There you go. Now keep in mind, you have to address the second hole. Just because it doesn't say anything about the second hole, you have to address it. So if he makes par on the first and third hole, but not the second, it does say something about the second, but not the second, then there you go. And I multiply all this together. I'll do that for you. Hold on. It gives me 0.1338848 is what my iPhone says, which is 0.1 to 3 decimal places, 3, 4, right? Because this is where I'm rounding, and this is the number I'm looking. And if that number is 5 or bigger, I have to round up. So a, say, 13.4% chance, or 134 thousandths of a probability that he will score par on the first, not par on the second, and then par on the third. And that wraps up the review. As always, please let me know if you have any questions, and have a good day.